Hi everyone, welcome back to Calc 2. Up to this point in Chapter 10, we have looked at some very specific type of series. We've looked at geometric and the telescoping series. What is unique about those two series is when they do converge, and we saw that geometric converges when the ratio, the R value, is less than 1. And then, of course, it diverges when the R value is greater than or equal to 1. But we can actually determine what it converges to by using the formula A over 1 minus R. And with the telescoping series, what we found is because so many terms cancel out, that you can expand the first couple terms and look at the last few terms and kind of see what's happening and see what's left, and you can actually get a sum. And you can see what your series converges to. That is not going to be the case with most series. So what we're examining through this entire chapter essentially is whether or not these infinite series that is put in front of you converges or diverges. Now, depending on what the series looks like, there are a lot of tests to determine that. So what I'm going to do is break down each test first and have its own video. So the first part of 10.4, we're going to look at what would essentially be the first test you would try on almost any series. And it's called our divergence test. All right, very basic test. So here's what the divergence test looks like. In some books or on the internet, you may actually see this as the nth term test as well. Sometimes it's called the nth term test. But basically, it states, and I'm going to write it in a way a little bit slightly different in the book, so it's the least confusing way. Let's put it that way. So it says if the limit of our series a to the n as n goes to infinity. So if we're able to take the limit of our series a to the n as n goes to infinity, and it does not equal 0, as long as it doesn't equal 0, then we can say that the summation as n goes from 1 to infinity of a to the n, the summation of our infinite series diverges. Okay, so very simply, you have a series, an infinite series from 1 to infinity of a to the n. If the limit as n goes to infinity of that series doesn't equal 0, you're done. You can say it diverges and you're finished with that problem. Now, here's the most important part I'm going to put in here. Otherwise, meaning if it does equal 0, the test is inconclusive. So what does that mean? That means if your limit does indeed equal 0, you cannot say it is convergent. Okay, your test is inconclusive. If the limit does indeed equal 0, you have to do further work to determine if it converges or if it diverges. So this test detects divergence only. It cannot detect convergence. So that simply means that when you do your test, as long as your limit is not equal to 0, you're done. Your limit equals 0, again, we're going to go through a lot of tests in this chapter. You have to apply something else to determine whether your infinite series is convergent or divergent. So let's look at a quick example. So take the sum in. We'll do k equaling 0 to infinity. I interchange. Sometimes I use k, sometimes I use n's of the series k over k plus 1. So you can see in this series I actually can let k equal 0 because my denominator is, my first term would simply be 0 over 1, which is a legitimate value. All right, so anytime, your directions are going to be quite simple. Determine whether your infinite series converges or diverges. That's all we're looking for. So any series you're given, you can quickly just try to apply your divergence test. So what does that mean? We take the limit as k goes to infinity of k over k plus 1. Well, we know how to take that limit. All right. You have a couple ways you can look at this. Your k values are both to the same power of 1, so that means you just need to take the coefficients 1 over 1. You can divide everything by k. Regardless of what you do, that limit equals 1. All right? Since the limit as k goes to infinity equals 1, 1 is not equal to 0, obviously. So what we state is by the divergence test, the summation k equaling 0 to infinity of k over k plus 1 diverges. So please note, I stated what test I used and gave a reason, and I showed that the limit did not equal 0, and then I stated by divergence test. These are the things I'm going to expect to see on your test. So please take the time to pay attention to how it's written and get in the habit of doing the same. Let's take a look at a second example. Summation all right. So again, you're faced with this problem. You need to determine whether it converges or diverges. So the first thing you can try is your divergence test. So we take the limit again. As k goes to infinity of 1 plus 3 to the k over 2k. All right, well, if you plug in k, you're going to get infinity over infinity. That's not going to help us. There's different things you can try. For this particular limit, one thing we can do is just break it up because we have one denominator, right? We can have 1 over 2k plus 3k over 2k, and actually I'm going to rewrite 3k over 2k as 3/2 k. As you plug in infinity, the first term is going to actually go to 0 because you're going to have 1 over an increasingly larger and larger number. And then your second term is going to go to infinity, so the whole thing goes to infinity. Well, guess what? Infinity is not equal to 0. So our divergence test works, and we can conclude that by divergence test, our series from 1 to infinity of 1 plus 3 to k over 2 to the k diverges. Okay? So we're going to circle back. And this will, again, it's kind of a great test to start with because you're done. You don't have to go any further. The problem is when it doesn't, when it does equal 0. So let's take a look at a couple examples that will then lead us into our next video. And there are 2 examples you should be pretty familiar with. All right. So here's the first one. Let's call this example 3. And we're going to do the summation. We'll use n's this time. N equaling 1 to infinity of 1 over n. All right. So when I say you should be familiar with this one, we looked at 1 over n back when we were looking at improper integrals. But now we're looking at 1 over n as a series. So we'll talk about that in a minute. But let's take a look. So if we try to apply our divergence test, we would have the limit as n goes to infinity of 1 over n. And you can see right away that that is going to equal 0, right? So right now we're going to say this test is inconclusive. All right? You cannot, remember, if it doesn't diverge, that does not automatically mean it converges. All this says is we can't determine what that does. All right, and we're going to come back to that, but let's look at a second example. So do the same thing with the limit as n goes to infinity of 1 over n squared. Well, isn't that still going to equal 0 because n's going to get increasingly larger and larger, and it still equals 0, which means our test is inconclusive. So let's just talk about these 2 series for one quick second, because I want to remind you that we're talking about series now, and we're not talking about integrals or functions. But we know, so what does 1 over n look like in a series? Right? Well, if I start at 1, I have 1, 1, right? 2, I have 1/2. Oops, sorry. 3. All right. It's going to look something like that. Well, let me make that a little bigger for a second. All right. Then 1/2. Sorry. Then 1/3, and 1/4, and so on and so on. And of course, the summation of 1 over n squared is similar. Instead of a half, it shoots down to a 1/4, and then it shoots down to a 1/9. And you recall, again, we worked with these as functions when we were looking at improper integrals. As a function now, because you've got to understand the difference. When we're talking about a series, we're talking about a discrete set of points. All right? When we're talking about a function of 1 over x, okay, then we're talking, right? We're talking that. And the function of 1 over x squared, it just went much quicker. We kind of talked about this. And if you recall, when we took the integral and we're looking specifically for the area under the curve, right? We found, if you recall, that the area under the curve for f of x equaling 1 over x from 1 to infinity actually diverged. But the area under the curve, because we found it went so much faster, this one converged to a value. So something similar is going to happen with our series. And we're going to use this connection between the series and the function. But before we move on to the next video, which will happen to have a test which is called the integral test, because it makes sense because we're going to actually look at the integrals. But I want to stop and point out that our original series is a discrete set of points. All right, we're just going to use the similarity to the integral and to that area to help solve it. Now, before we move on, I also want to mention that this particular series, not example 4, but this one, we will talk about, that has a special name, 1 over n. It is called the harmonic. And that harmonic series is simply 1 plus 1/2 plus 1/3 plus 1/4 and so on and so on. So again, divergence test is great if when you take your limit, you do indeed get a value that is not 0. But the second you get a value that is 0, your divergence test becomes inconclusive and you need to move on to a different test. And that test you move on to will really depend on what the original series looks like. So in the next video, we're going to take a look at something called our integral test, and we're going to pick up with this particular problem.